Hello everyone. Today I'm going to talk about one of Alladi's formulas, which is related to the prime number theorem. I gave a talk on this topic in the Parajumpalized conference last week. So if you attended that conference, then you're good to go because those two talks are same. First, let's look at what the formula is. Here are some notations. Z of S is the Riemann-Zeta function. P of n is the Mobius function. Small p of n is the smallest prime factor of n, and capital P of n is the largest one. It's well known that the prime number theorem is equivalent to this convergence. And if we take the first term, which is 1, to the right-hand side, then we can rewrite it as follows. Alladi refined this formula. He proved that if L and K are co-prime integers, then the following restricted sum is 1 over 5k. Here, phi is a original tangent function, and this sum is restricted over integers whose smallest prime factors p of n are in the arithmetic progression modulo k. So this formula is like the prime number theorem in arithmetic progressions. Thus, first generalized these formulas to the setting of Galois extensions. Let's look at what they did. Here are some notations. K over Q is a valid Galois extension over Q, and G is the Galois is its Galois group, and K over Q over script P is an Artin symbol, which is an element in the Galois group that corresponds to the Frobenius map. And then K over Q over small p is a collection of the Artin symbols for script P that's over small p for unramified p. So this collection is a conjugate class of the Galois group G. Thus, they proved that for any fixed conjugate class C, we have the following formula. So the right-hand side is the cardinality of C over the cardinality of G. So this ratio is related to the Chavatar density theorem, and the sum is restricted over the integers, which is satisfy the following identity. So the the collection of Artin symbols must equal to the fixed C. Okay, so this is the Dawson's formula. Alladi's formula is a special case of Dawson's formula. If you take K to be the cyclotomic field and say the conjugate class of L. Second, Sweetin and Wu generalized the Dawson's formula to number fields. Okay, recently, Kuro McDonald and Sa generalized all those results to natural density. Let's look at what they proved. P is the set of all primes, and S is a subset of P. Delta of S is the natural density of S in P. And they proved that if S has a natural density, then the sum for mu of n over n, which is restricted over integers whose smallest prime factors p of n in S, then this restricted sum would be exactly the natural density of S. So this is their formula. And here are some remarks. Actually, their work is over arbitrary number fields. This is just the basic case for rational field. Second, if you take S to be a set of arithmetic progression, then you will get Alladi's formula. And then if you take S as follows, then by the Cherepanov density theorem, you will get Dawson's formula. Okay, so my goal is to prove some analogues for those results. And here is my observation. First, we know that the Dirichlet series of the Mobius function is the reciprocal of the Riemann function, and then the limit of this reciprocal to 1 from the right hand side is 0. So the numerator here is 1. The observation is if we replace the numerator 1 by a function which is absolutely convergent and s equals to 1, then the following limit still holds. And then if we write out the Dirichlet series for this fraction, then a natural question is, do we still have the Alladi's formula? So in other words, what if we replace the numerator mu of n by other arithmetic functions in Alladi's formula? In general, the answer is no. Here's a counterexample. So you can check that this formula is wrong, is false, if you take f of s to be to the power negative s. However, for many interesting functions, the answer is yes. So last year, I proved 2 functions, the neural function and the Ramanujan sum. So here, look at that. So actually, for the neural function and the Ramanujan sum, they are by their Dirichlet series. So those 2 functions can be written as the differential convolutions of the Mobius function with some good arithmetic functions. So this year I try to generalize those two examples to general arithmetic functions. So here's my main result. Suppose that the arithmetic function a satisfies the first term is 1 and the following convergence condition. So this convergence condition basically means that the differential series of A is absolutely convergent and S equals to 1. So if for A satisfies those two conditions, then we can prove that if S has a natural density, then the following Alladi formula holds for mu convoluted by A. So here mu star A means the differential convolutions between mu and A. So so now a good thing is we can prove the following corollary. So under a weaker condition, we can replace the denominator n in Alladi's formula by phi of n. Phi is the Euler's torsion function. In particular, we get that if L and K are co-prime integers, then the following two formulas hold. So here, C sub n of m is the Ramanujan sum. Here, m is fixed and n varies. So, and those two formulas will find the following hard disk formula in 1921. So those two formulas are like Alladi's formula. Okay, so here are some examples. So first, let lambda be a multiplicative function that which is bounded by 1 and takes value negative 1 for every prime. Then we can get the following Alladi's formula. So, by the way, I call all the results, also all the formulas before as an Alladi's formula. Here are some examples for the lambda. For example, you can take lambda of n to be the Neuer function, negative 1 to the omega of n, and negative 1 to the capital A of n. So here, omega of n is the number of distinct prime factors of n, and capital A of n is an additive function which was introduced by Alladi and Ehrlich in 1977. So actually, negative 1 to the a of n is the first example I studied. Second, we can get the following formula. So here m is fixed, and the point is that Biao of m n. So this means that n has to be co-prime to m. And thirdly, we can we can replace the denominator n in Alladi's formula by the functions multiplicative functions that are near to n. So here g is a multiplicative functions that's near to n, which means that the value at prime p is close to p. So then for such functions, we can get the following Alladi's formula. So here are some examples for g of n, and you can take g of n to be the Dedekind precise function, and the sum of divisors function, and the following normalized sum of divisors function of power k. And if k, if you take k to be 3 and 7, then this this function is related to the E8 lattice and the E16 lattice. And the last example is related to R4 and R8. So here the R sub k of n is the number of ways representing n and the sum of k squares. Here, if k is 4 or 8, then we have following explicit expressions for them. A natural conjecture is the formula here. The formula 5 also holds if you replace mu by the general functions like the lower function and the Ramanujan sum. Finally, I'd like to talk about some conjectures. First, so in previous examples, they are related to the reciprocal of the Riemann function. Actually, we can consider the following: the m for the convolution of the Mobius function. Then we conjecture that the Alladi's formula should also hold for those functions which is related to the m-fold of the Mobius function. And the point is that so in this case m is greater or equal than 2. So in previous case m is 1. So this is very different from the from our main result. So here are some examples for mu. And you can also consider the higher. So in previous case, the power is an integer. You can also consider the positive real power, and you can also propose a similar analogy, but it's very hard. Finally, we can also generalize the lateral density to relative lateral density. So here, capital P is a set of some primes, so not all primes, and the angle bracket of P is the multiplicative semigroup generated by P, and for subset of S of P, we can also define the lateral density delta of S in P as follows. Then our conjecture is that if the reciprocals of P over the primes in P, so if the sum of those reciprocals diverges, then we conjecture that we also have the Alladi formula. So here, if S equals to capital P, then delta sub P of P is 1. Then this formula is appears in the paper of Tao's formula in 2010. So this formula is like a hybrid of Tao's formula and Alladi's formula. So okay, that's the end of my talk. Thank you for listening.